There is a heart on Pluto. Not a metaphor, a physical feature. 1 million square miles of nitrogen ice, shaped like a valentine, bright enough to see from 1 billion kilometers away. It is so heavy it tilted the planet. A spacecraft spent 9 years getting there. One shot, no second pass, and 10 days before arrival, the entire flyby computer system crashed. The team had 72 hours to rebuild it from nothing. They had 4 hours to spare. The mountains on Pluto are made of water ice, and they float. There is a volcano, not lava, ice, a dome 150 kilometers across, a central pit at the summit. Scientists believe it erupted within the last billion years, on a world everyone assumed was dead. The surface of the Great White Plain has no craters, not one, in a part of the solar system where impacts have been accumulating for 4 billion years. This plain has been completely renewed. Within the last 10 million years, something is still doing it. Beneath that plain, nitrogen ice moves in slow churning cells, warm material rising from below, cooling, sinking, rising again, in a cycle that takes 500,000 years to complete one turn. A lava lamp made of frozen air, running right now. The atmosphere is 10 microbars, 100,000th of what you breathe. And it is blue. There is a moon half the size of the planet. It did not form the way moons usually form. Two worlds collided. They stuck together for 10 hours, rotating as a single snowman-shaped body. Then they separated and have been locked face to face ever since. Beneath Pluto's ice, the models say there is liquid water, an ocean, kept from freezing by insulating layers of methane hydrate ice. In the dark, in the cold, at the edge of everything. The signal confirming the flyby had worked took 4 hours and 25 minutes to reach Earth. A 15-minute stream of data. People stood in a room in Maryland and wept. That was July 15th, 2015. We have been studying what that spacecraft found ever since. This is the story of a world stripped of its name, exiled to the dark beyond Neptune, and then, when we finally looked, revealed as one of the most geologically complex, atmospherically active, internally alive objects in the solar system. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now imagine Pluto orbits the Sun at an average distance of 39.5 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, approximately 149 million kilometers. Multiply that by 39.5. That is where Pluto lives. At that distance, sunlight takes 5.5 hours to arrive. The Sun, seen from Pluto's surface, is not a disk of warmth. It is a bright star, the brightest in the sky, but a star. It provides roughly 900 times less heat than it gives to Earth. Pluto is not alone out there. It inhabits a region called the Kuiper Belt, a vast donut-shaped disk of frozen material extending from roughly 30 to 50 astronomical units from the Sun. The Kuiper Belt contains hundreds of thousands of icy bodies, dwarf planets, and perhaps trillions of comet nuclei. It is the debris field left over from the formation of the solar system, the material that never quite accumulated into a full planet because Neptune's gravity kept stirring it, preventing it from settling. Pluto is the largest known object in this belt, but it is surrounded by kin, Eris, Makemake, Haumea, worlds of ice and rock, ancient and cold, orbiting in the dim light beyond Neptune. You are out there now. Not on Pluto yet, not close enough to see the heart. You are simply in the dark, in the quiet beyond the last giant planet, watching the sun grow faint. The temperature out here drops toward 38 Kelvin. That is 235 degrees below 0 Celsius. At this temperature, nitrogen does not behave the way it does on Earth. It is not a gas here. It freezes. It pools into sheets and basins. It flows slowly over geologic time, like a glacier made of something you could breathe on a warmer world. Pluto was not always known. It was discovered on February 8, 1930, by a 24-year-old astronomer named Clyde Tombaugh at the Lowell Observatory in Flagstaff, Arizona. Tombaugh had been given an assignment: blink through thousands of photographic plates taken on separate nights, looking for any point of light that moved against the background stars. A moving light meant a solar system object. He spent months doing this by hand, plate after plate, night after night, scanning the sky in a machine called a blink comparator, which rapidly alternated between two images so that any movement would appear as a flicker. On that morning in February, one point of light flickered. It was found in the constellation Gemini, where predictions had suggested a ninth planet might exist. Tombaugh's discovery was announced to the world on March 13, 1930, the 75th anniversary of Percival Lowell's birth, the astronomer who had originally predicted the planet. A flood of naming suggestions arrived. The name Pluto, proposed by an 11-year-old girl in Oxford, England, named Venetia Burney, was chosen because it fit, the Roman god of the underworld, a world unseen in permanent darkness, and because the first two letters honored Percival Lowell. For the next 76 years, Pluto was a mystery. Even the Hubble Space Telescope could only resolve it as a fuzzy blob of pixels, a smeared shape with hints of light and dark. Its size was uncertain. Its internal composition was estimated, but not known. Scientists knew it had nitrogen ice on the surface. Spectroscopic observations in the 1990s confirmed that. They knew it had an atmosphere that thickened when it was closer to the sun and collapsed as it moved away. They knew it had at least one moon, Charon, discovered in 1978. But that was almost everything. Everything else would have to wait for a spacecraft. The decision to build that spacecraft was not easy. NASA received the proposal for what became New Horizons in the 1990s, and it was initially rejected. Budget pressures, competing priorities, arguments about scientific value. Pluto advocates, led by a scientist named Alan Stern at the Southwest Research Institute, fought for years to get the mission approved. The argument was simple and devastating. Pluto's atmosphere was freezing. As Pluto moved away from the sun on its 248-year orbit, its surface temperature was dropping, and the thin nitrogen atmosphere was beginning to collapse back onto the ground. If a spacecraft was not launched in time, it would arrive to find an airless, frozen world with far less to study. The window was closing. The mission was approved. New Horizons was built. On January 19, 2006, at Cape Canaveral, Florida, an Atlas V rocket lifted off carrying a spacecraft the size and weight of a grand piano. It was launched at a speed of 16.26 kilometers per second, fast enough to leave Earth's gravity without any additional propulsion. It was, at that moment, the fastest human-made object ever launched from Earth. You watch it rise. The exhaust column spreads white against a January sky. The rocket shrinks to a point of light, then disappears. The spacecraft inside it, carrying 7 scientific instruments, a small piece of Clyde Tombaugh's ashes, an American flag, and a CD containing the names of 434,000 private citizens who had signed up to send their names to Pluto, is already moving faster than any spacecraft has ever moved at launch. The 7 instruments aboard New Horizons have specific purposes, and each one is tuned to a different aspect of the Pluto system. LoRa-I, the Long-Range Reconnaissance Imager, is a telescopic camera designed to take the highest resolution images of Pluto's surface. Ralph is a color imager and infrared spectrometer, mapping the distribution of surface ices. Alice is an ultraviolet spectrometer for studying the atmosphere. Rex, the radio science experiment, will measure the atmospheric temperature and pressure profile by observing how Earth's radio signals bend as they pass through Pluto's atmosphere during the occultation. Pepsi and SWAP measure particles in the space around Pluto, and SDC, the student dust counter, built by university students, measures dust particles along the entire trajectory. Every instrument has a story. Every instrument represents years of design, testing, calibration, and concern. The entire spacecraft operates on less than 200 watts of electrical power, less than most household light bulbs. Its power comes from a radioisotope thermoelectric generator, a device that converts the heat of decaying plutonium-238 into electricity, with no moving parts, no solar panels, no batteries that need sunlight. At 39 astronomical units from the Sun, solar panels would be useless. The Sun is simply too far away. The spacecraft weighs 478 kilograms fully fueled. Its largest component is a 70-centimeter parabolic antenna, a dish pointed back toward Earth, through which it will transmit everything it learns, everything it sees, everything it measures in those 9 days over Pluto, that entire archive of a world no spacecraft has ever visited before, compressed and encoded and sent home at 1 kilobit per second across 32 astronomical units of vacuum. Its trajectory takes it past the asteroid belt, past Jupiter. In February of 2007, New Horizons makes a close pass of Jupiter, not to study it, but to steal a fraction of its momentum. The gravity assist maneuver accelerates the spacecraft by approximately 14,000 kilometers per hour, trimming 3 years off the journey. During the Jupiter flyby, New Horizons does real science, imaging the planet's storms, its ring system, its moons, but Jupiter is not the destination. Pluto is. Always Pluto. After Jupiter, the spacecraft enters hibernation. Most of the next 7 years, New Horizons sleeps. Its systems are powered down to preserve them. Once a week, it transmits a brief tone back to Earth, a heartbeat signal confirming it is still alive. Mission controllers receive this tone, noted in their logs, and wait. The spacecraft drifts in the dark, cold, and quiet, covering approximately 1 million kilometers every single day. You drift with it. Consider what that means. 1 million kilometers per day. The distance from Earth to the Moon is 384,000 kilometers. New Horizons covers that distance in roughly 9 hours. It covers 1 full astronomical unit, 149 million kilometers, in approximately 5 months. And still it takes 9.5 years to reach Pluto. The solar system is incomprehensibly large. We speak of distances in astronomical units because the numbers in kilometers are too large for intuition to hold. 39.5 astronomical units, Pluto's average distance from the Sun, translates to approximately 5.9 billion kilometers. Even at New Horizons' extraordinary speed, the journey takes nearly a decade. The hibernation is not complete silence. Once a week, that heartbeat tone. Once a year, a more detailed health check. Systems brought briefly online, instruments powered up and tested, telemetry reviewed. Scientists watch the data from those checkups the way doctors watch vital signs, looking for anomalies, for degradation, for anything that might indicate a problem developing in the darkness between planets. There are no anomalies. The spacecraft performs exactly as designed. The years pass on Earth. New Horizons crosses the orbit of Saturn in 2008, the orbit of Uranus in 2011, the orbit of Neptune in 2014, the first spacecraft to cross Neptune's orbit since Voyager 2 in 1989, 25 years earlier. Each milestone is noted in the mission logs, marked with the quiet satisfaction of mathematics fulfilled. The spacecraft is exactly where the equations predicted it would be. There is nothing out here but vacuum, particle density less than 1 atom per cubic centimeter, and the long, patient arithmetic of orbital mechanics. New Horizons is falling toward Pluto the same way a stone falls toward the Earth, except that Pluto is 32 astronomical units away and the stone is a piano. On December 6, 2014, New Horizons is brought back online. The hibernation ends, instruments are checked, calibrations are run. The spacecraft begins approaching Pluto from a distance of 220 million kilometers, farther away than Earth is from the Sun, and already its cameras are returning better images of Pluto than anything the Hubble Space Telescope could provide. The team begins to see the heart for the first time, a bright region, Western Hemisphere, vaguely symmetrical. It grows in the images over the following weeks. And then July 4th, 2015, 10 days before closest approach, a catastrophe. The spacecraft goes into safe mode. An overload in the computer system, the main processor and the navigation processor, were both trying to access the same data at the same time, creating a conflict that triggered an automatic shutdown of all science operations. New Horizons is now 9 hours signal travel time from Earth, 4.5 hours for a command to reach it, 4.5 hours for a response to return. There is no such thing as a quick fix at this distance. The flyby sequence, a precisely choreographed set of 9 days of observations, every instrument movement pre-planned and stored in the spacecraft's memory, had been partially wiped. It would need to be rebuilt, tested, and uploaded within 72 hours, or the flyby would be wasted. 9 years of travel, billions of dollars, one shot, and the window was closing at 50,000 kilometers per hour. The team works without stopping. Engineers, scientists, navigation specialists, 72 hours of continuous effort, rebuilding the command sequence from scratch. They do not have the luxury of sending a test version first. Every command must be correct on the first try, because there is no time to fix errors. With 4 hours to spare before the flyby sequence was scheduled to begin, the rebuilt software is uploaded. The spacecraft wakes. It begins to execute the sequence, and it works. The scale of what that means is worth sitting with. A team of engineers, sleep-deprived and under pressure that no professional situation on Earth could simulate, rebuilt the command architecture for a 9-day scientific campaign from scratch, tested it as rigorously as time allowed, and transmitted it across 9 light hours of space. The engineers could not go to the spacecraft. They could not touch it. They could not see it. All they had was mathematics, software, and a radio signal that took 4.5 hours each way. And they did not fail. Alan Stern described it later as the hardest thing he had ever seen accomplished in spaceflight operations. The team named the crisis and its resolution simply as a testament to what the mission meant to the people who built it. They had spent 15 years working toward a single moment, and when that moment was threatened, they did not stop. On July 14, 2015, at 11:49 UTC, New Horizons passes 12,500 kilometers above the surface of Pluto, closer than the distance between London and Sydney, Australia, at a speed of approximately 14 kilometers per second. It is traveling so fast that it crosses the entire Pluto system in less than 3 minutes. During those 3 minutes, and throughout the 9-day flyby sequence, the spacecraft takes thousands of images and records terabytes of scientific data, but it cannot send the data home at the same time as it is collecting it. Not at this distance, not at this data rate. The transmission speed from New Horizons back to Earth is approximately 1 kilobit per second, slower than dial-up internet from the 1990s. At that speed, sending the complete dataset takes 16 months. The first signals confirming a successful flyby arrive at Mission Control at Johns Hopkins University at 12:53 UTC on July 15th, 13 hours after closest approach, a 15-minute burst of status information. When the signal is received, people stand in the room and applaud. Some of them cry. The lead scientist holds up a photograph. It shows a world with a heart. In, hold, out. That image, the first true view of Pluto's surface, was taken from 250,000 kilometers away, the day before closest approach. It shows a world that nobody expected. Mountains, plains, color, not just gray, but muted rust and cream and ivory, and the heart, bright, smooth, impossible. You are looking at something no human being has ever seen before. The heart is called Tumbling Regio, named for the man who found the planet. It stretches across more than 1 million square miles of Pluto's equatorial region, a bright, elevated feature, roughly shaped like a valentine, divided down the center by a line of low mountains into 2 distinct halves. The western half is the one that dominates the view, smooth, featureless, almost blindingly white against the darker surrounding terrain. No impact craters, not a single one visible at New Horizons resolution. The absence of craters means something important. In the outer solar system, where impacts from Kuiper Belt objects are slow but steady over billions of years, a heavily cratered surface is old, billions of years old. A surface with no craters is young, geologically young, astronomically recent. That smooth white plain to the west of Tumbling Regio, what will later be formally named Sputnik Planitia, has been resurfaced, renewed, or erased within the last 10 million years. On a world 3 billion miles from the sun, something is actively reshaping the surface. This is the discovery that changes everything. Because Pluto was not supposed to be active, it was supposed to be dead, a frozen remnant, geologically inert, a world that had exhausted whatever internal heat it ever had billions of years ago, and simply stopped. That was the assumption, that was the expectation. And it is wrong. The mountains surrounding the smooth plain are made of water ice, not nitrogen ice, not methane ice, but water. At Pluto's surface temperature, water ice is not liquid and never has been. It is rigid, structural, load-bearing, as hard as granite on Earth. These mountains rise between 1 and 3.5 kilometers above the plain. Some of them are named the Hillary Montes to the southwest, the Tenzing Montes rising further south, named for the two climbers who first reached the summit of Everest. And at the margin where these mountains meet the smooth plain, something extraordinary. The mountains appear to float. Not metaphorically, structurally. Water ice is slightly less dense than nitrogen ice. Where chunks and blocks of water ice sit in contact with the nitrogen ice of the plain, the nitrogen, over geologic time, flows and shifts beneath them, and the water ice blocks rise upward, buoyed by the denser material beneath, like icebergs in a frozen nitrogen sea. The mountains are moving, not at any speed you could observe in a human lifetime, but moving, drifting slowly across the plain, carried by the flow of ice beneath them, the same way pack ice carries debris across an Arctic ocean. You are standing on the edge of this plain now. The light is dim, not dark, but not like any sunlight you know. The sun is a brilliant point, 39 times farther away than it is from Earth. It illuminates the surface enough to see, but there is no warmth in it. The temperature around you is minus 228 degrees Celsius. At this temperature, nitrogen is a solid beneath your feet. The ground has a faint tan color where the older terrain meets the edge of the plain, and then past that boundary, it opens up white and vast and still. You are looking at the largest glacier in the solar system. You will spend the next part of this story inside it. Now, let us step into this moment. Before the details of what Sputnik Planitia is and how it moves and what drives it from below, before all of that, there is the question of what it felt like for the scientists on Earth to see Pluto for the first time. Not what it looked like, what it felt like. Every person who worked on the New Horizons mission had spent years, some of them more than a decade, working toward a moment they could not be certain would come. The spacecraft might have failed, the flyby software crisis might not have been resolved in time, an instrument might have malfunctioned, any of 100 engineering risks might have terminated the mission before it reached its target. They had planned for success and tried not to imagine failure, but failure was always possible. And then the images started arriving. Not all at once, not in a dramatic flood. They trickled in at 1 kilobit per second, agonizingly slow, pixel by pixel, image by image, over 16 months. The first high-priority datasets were selected and transmitted in the days immediately after closest approach. The rest came later. Scientists had to wait months to see some of the images that were taken in the first minutes after the flyby. But what they saw immediately was enough. Pluto's diameter, first of all, 2,370 kilometers. This was larger than any previous measurement had suggested. For decades, estimates of Pluto's size had ranged widely because it was too small and too far away to measure precisely from Earth. The Hubble Space Telescope had given rough dimensions, but with significant uncertainty. Now New Horizons confirmed, Pluto is the largest known object in the Kuiper Belt, approximately 18.5% the diameter of Earth, slightly larger than the dwarf planet Eris, which had briefly held the title and contributed to Pluto's reclassification. The reclassification deserves a moment. In 2006, the same year New Horizons launched, the International Astronomical Union met in Prague and voted on a formal definition of the word planet. The definition required a body to orbit the Sun to have sufficient mass for gravity to pull it into a roughly spherical shape, and to have cleared the neighborhood of its orbit of other debris. Pluto fails the third criterion. It orbits within the Kuiper Belt, surrounded by thousands of similar objects. Under this definition, Pluto became a dwarf planet, a member of a new category that also includes Eris, Haumea, Makemake, and others. The vote was controversial then. It remains controversial now. Many planetary scientists, including Alan Stern, the principal investigator of the very mission that studied Pluto, disagree with the definition on both philosophical and scientific grounds. Under the geophysical definition favored by many researchers, any body massive enough to be spherical under its own gravity is a planet, which would include Pluto and potentially dozens of other solar system objects. The debate continues in the scientific literature. What is perhaps most striking about the reclassification is that it happened in the same year the spacecraft designed to explore Pluto finally launched. The planet was demoted as its explorer left the launch pad, and then 9.5 years later, that explorer arrived and revealed a world so geologically complex, so atmospherically dynamic, so surprising in its activity, that the scientists studying it were left with a simple question: if this is what a dwarf planet looks like, what else might we have been wrong about? The answer, it turned out, was quite a lot. What is not in dispute is what New Horizons found. The surface of Pluto, seen close for the first time, is one of the most geologically diverse in the solar system. New Horizons mission member Jeff Moore described it as every bit as complex as the surface of Mars, and Mars, with its Olympus Mons and its Valle Marineris, and its ancient river deltas, and its current atmospheric chemistry experiments, is not a simple world. You begin to walk it. The terrain immediately surrounding Tumba Regio varies dramatically by direction. To the north and east, ancient, heavily cratered highlands. The craters here are billions of years old, deep eroded, their rims softened by whatever atmospheric deposition and sublimation processes have operated over geological time. The age of this terrain is read in its craters, the same way age is read in tree rings. More craters means more time, more accumulated impacts, more exposure to the slow bombardment of the Kuiper Belt. Moving south and east, the terrain changes. You pass through what mission scientists informally named the bladed terrain, Tartarus Dorsa, a region covering hundreds of thousands of square kilometers, where the surface is not flat but sculpted into long parallel ridges of methane ice, hundreds of meters tall, oriented north to south. From above, this terrain looks like the skin of a pineapple, or like a field of enormous fins, or like the ridges on the back of some vast creature. These structures are called penitents, a term borrowed from a terrestrial phenomenon on Earth at high altitudes in the Atacama Desert and on certain glaciers in the Andes. Sunlight striking ice at a low angle can cause uneven sublimation, carving the ice into thin, upright blades that can reach a few meters in height, aligned to face the sun. On Pluto, the same process operates, but the scale is different by 2 orders of magnitude. Pluto's bladed terrain features structures hundreds of meters tall, spaced roughly 30 to 70 kilometers apart. The mechanism is the same. Methane ice sublimes preferentially from certain faces, depending on the angle of sunlight, leaving behind the ridges that did not sublime. The consistent north-south orientation of the blades tells scientists something important. Solar illumination is the dominant factor shaping this terrain, more powerful than wind, more powerful than internal heat, more powerful than impact gardening. The Sun is shaping Pluto's surface even from 39 astronomical units away. You move toward Tumba Regio. As you approach the edge of Sputnik Planitia, the terrain transitions. The dark cratered highlands give way to the margins of the Great Plain, a boundary marked by the Aladrisi Montes to the northwest, a chaotic region of jumbled blocks of water ice, some of them kilometers across, piled against the edge of the basin like debris pushed by a slow tide. Planetary scientists believe these blocks were once part of the highlands that bordered the basin, and that the collapsing edge of the ancient terrain, undermined perhaps by the weight of accumulating nitrogen ice, broke apart and slid inward. The nitrogen ice plain itself begins here, and the first thing you notice is that it does not look like a plane in the way you might imagine, perfectly flat, featureless, mirror smooth. It is not. Looking across the surface of Sputnik Planitia, you can see that it is divided, not by cracks or ridges, but by shallow troughs forming an irregular pattern of polygons. Each polygon is on average 33 kilometers across. Some are rounder, some more angular, but they tile the surface of the plane the way cells tile living tissue, irregular but systematic, a pattern that repeats across thousands of square kilometers. These are convection cells. To understand what you are seeing, you need to know what is happening below the surface of the plane. The basin of Sputnik Planitia is filled with nitrogen ice to a depth of at least 4 kilometers, possibly deeper toward the center. Beneath that nitrogen ice, Pluto's interior is still generating a small but measurable amount of heat. The source of this heat is the slow radioactive decay of elements in Pluto's rocky core, uranium, thorium, potassium isotopes that have been decaying since the solar system formed, releasing energy at an extraordinarily low rate, but doing so continuously, steadily, across billions of years. This heat warms the bottom of the nitrogen ice layer. Warm nitrogen ice becomes slightly buoyant. It rises. The rising warm ice reaches the surface, where it radiates heat into the cold atmosphere and becomes dense again. Then it sinks back down, displaced by the next rising cell of warm ice from below. This is convection, the same process that drives Earth's mantle, that moves tectonic plates, that creates the circulation patterns in the oceans. On Earth, it happens in rock and water. On Pluto, it happens in ice that is so cold it would shatter if you struck it with a hammer. And yet, over geological time, it flows like a slow, viscous fluid. The cycle takes approximately 500,000 years. That is how long it takes for one complete overturn of the nitrogen ice, for warm material from the base of the 4-kilometer column to rise to the surface, cool, and sink back down again. Compared to Earth's mantle convection, which takes tens to hundreds of millions of years per cycle, this is rapid. Pluto's nitrogen ice is not as viscous as rock. It moves. The surface you are standing on is moving, right now, at a rate you could not observe in a human lifetime, but moving. The troughs between the polygons mark the boundaries where cold ice is sinking. The centers of the polygons mark where warm ice is rising. The surface has no craters, not because impacts don't happen, but because any crater that forms on this plane is slowly consumed, obliterated, overturned by the convective cycle before it can accumulate. The oldest surface feature in Sputnik Planitia is less than 10 million years old. In geological terms, this surface was renewed yesterday. Now you look at the atmosphere above the plane. Pluto's atmosphere is thin, almost unimaginably thin by Earth standards, The surface pressure is approximately 10 microbars, which is 100,000th of Earth's atmospheric pressure at sea level. You could not breathe it. You could barely detect it with most instruments. It is the kind of atmosphere that on Earth would be called a near vacuum. And yet it is layered and complex and actively doing things. The primary constituent is nitrogen, the same gas that makes up 78% of Earth's atmosphere, but at Pluto's surface temperature of roughly 45 Kelvin, most of that nitrogen is frozen solid in the plains and highlands below. What is in the atmosphere is the tiny fraction of nitrogen that is sublimed, transitioned from ice to vapor in response to the faint warmth of sunlight. Mixed into the nitrogen are methane and carbon monoxide, both in small quantities. Methane is important. In Pluto's stratosphere, at an altitude of around 20 to 40 kilometers, methane absorbs solar radiation and generates heat. This creates a thermal inversion, a warm layer in the stratosphere above a colder surface, which is the opposite of what you might intuitively expect. The surface is colder than the air above it. The temperature at the surface is roughly 45 Kelvin. At an altitude of 30 kilometers, it rises to approximately 110 Kelvin. Then it slowly decreases again with height. Even more surprising, the atmosphere extends high above the surface. Nitrogen absorption begins at an altitude of 1,670 kilometers, methane at 960 kilometers, hydrocarbon compounds at 420 kilometers. The haze layers, thin veils of complex organic particles called tholins, created when ultraviolet radiation from the sun breaks apart nitrogen and methane molecules, and they recombine into more complex chains, extend up to 200 kilometers above the surface. You can see these haze layers from the surface. They are blue. When New Horizons looked back at Pluto after the flyby, a view of the planet backlit by the sun, its thin atmosphere silhouetted against darkness, the haze layers scattered the sunlight in a way that made them appear distinctly blue. This was unexpected. The tholins that form Pluto's haze should, by themselves, produce a brown or red color. The blue comes from the particle size of the tholins, small enough to scatter short wavelength light, the same way Earth's atmosphere scatters blue light to make the sky. Pluto has a blue sky. Not a warm blue, not a welcoming blue, the blue of an atmosphere so cold and thin that each breath of it would freeze your lungs in the time it takes to inhale. But blue, a pale, steady blue at the edges of the planet when the sun is behind it, the same color as the sky over Earth, born from the same physical principle, on a world where everything else is foreign. The tholins that produce this haze are more than just an optical phenomenon. They are the product of chemistry. When ultraviolet radiation from the sun, even the reduced ultraviolet at Pluto's distance, strikes nitrogen and methane molecules in the upper atmosphere, it breaks them apart. The fragments recombine into more complex molecules: acetylene, ethylene, ethane, hydrogen cyanide. These heavier compounds drift downward, eventually settling onto the surface, contributing to the reddish-brown coloring that gives parts of Pluto's terrain their distinctive warm tones. The tholin layer on the surface is thin, a coating, not a deep deposit, but it is enough to change the color of the water-ice bedrock beneath, from white to the muted rusty tan you see in the darker highland regions. The chemistry happening in Pluto's atmosphere is the same family of chemistry that operates in Titan's atmosphere, the thick nitrogen atmosphere of Saturn's largest moon. Scientists studying Titan have worked for decades to understand Tholin formation, and those models apply directly to Pluto. The outer solar system is not a collection of isolated, unrelated environments. It is a connected set of chemistry experiments, each running slightly different conditions, each producing variations on the same underlying processes. You sit with that for a moment. You are on Pluto. The sun behind you is a bright star. The haze above you is blue. The ground beneath you is nitrogen ice, 4 kilometers deep, slowly turning in convection cells that take 500,000 years to complete one cycle. The air pressure is less than 100,000th of what you breathe at home. The temperature hovers near 45 Kelvin, cold enough that nitrogen freezes solid beneath your feet. And this world is alive. Not in the biological sense, not in the way that life is alive, but geologically alive, internally active, atmospherically dynamic, surficially renewing itself on timescales short enough to matter in a solar system that is 4.5 billion years old. The nitrogen in the heart of Pluto goes through a daily cycle. During Pluto's day, which lasts 6.4 Earth days, the side facing the sun receives slightly more solar energy than the side facing away. This tiny difference in heating is enough to cause measurable sublimation of nitrogen ice from the sunlit portions of Sputnik Planitia, releasing nitrogen vapor into the atmosphere. As Pluto rotates, that same region moves into shadow, cools, and the nitrogen vapor condenses back onto the surface. The heart breathes. Every 6.4 Earth days, in and out, nitrogen rising and falling, subliming and condensing, driving a weak but measurable circulation in the atmosphere that scientists describe as analogous to the way Earth's ice sheets in Greenland and Antarctica influence global climate patterns. Sputnik Planitia is not just the largest geological feature on Pluto, it is the engine of Pluto's climate. And it is there because of something that happened 4 billion years ago. The basin of Sputnik Planitia, the depression in which all that nitrogen ice has accumulated, was not carved by the ice itself. It was carved by an impact. Approximately 4 billion years ago, a Kuiper Belt object somewhere between 50 and 100 kilometers in diameter struck Pluto at this location, gouging out a basin that is now 1,400 kilometers wide and 1,200 kilometers long. That impact, or the geological consequences that followed, set in motion every process you are seeing tonight. The ice accumulated in the basin because the basin was a cold trap. Lower than the surrounding terrain, it collected sublimated nitrogen from elsewhere on Pluto's surface. As more ice accumulated, it reflected more sunlight, which kept it cold, which attracted more ice, a runaway albedo cycle that continued until the basin was filled to its current depth. And then the ice became so heavy, so massive an accumulation in one location, that it changed Pluto's rotation. A mass of nitrogen ice 4 kilometers thick over an area more than 1 million square miles in size is not evenly distributed around the planet. It creates a gravitational anomaly, an imbalance in the distribution of mass. Pluto responded to this imbalance the same way any rotating body responds to a shift in its mass distribution. It reoriented. The planet tipped, slowly over geological time, until Sputnik Planitia aligned with the tidal axis connecting Pluto to Charon. This process, the reorientation of a planetary body's spin axis in response to internal mass redistribution, is called true polar wander. It has occurred on Earth, it has occurred on Mars. It is rare and requires either a very massive feature or a relatively thin, mobile lithosphere. Pluto has both. The heart moved the planet. Let that settle. The image of a glacier so massive it reoriented an entire world. Not through any sudden event, not through an explosion or a collision, but through the slow, patient accumulation of ice over geological time, nitrogen vapor drifting on weak winds, settling into the lowest, coldest basin, layer by layer, year after year, over millions of years, until the weight of it was sufficient to tip the planet's spin axis, to make Pluto lean toward its moon and stay there. There is no human parallel for this, no event in recorded history, no structure ever built, no process ever industrialized comes close to the physical scale of what nitrogen ice did to Pluto simply by accumulating in a basin. The pyramids of Giza took decades to construct and weigh approximately 6 million tons. Sputnik Planitia's nitrogen ice weighs, conservatively accounting for density and volume, several billion trillion kilograms. It is a mass so large it bent the rotation of a planet. And it built itself, molecule by molecule, winter by winter, across timescales that make the age of human civilization irrelevant. This is what the science tells you, not as a metaphor, as measurement, as calculation, as the straightforward arithmetic of mass, density, volume, and gravitational torque. You are lying on the surface of Sputnik Planitia now. The convection cells move so slowly beneath you that the surface feels still. The haze layers above glow faintly blue in the starlight. The mountains to the west, Hillary Montes, Tenzing Montes, the Al-Idrisi Montes to the north, stand silent and enormous, their water ice summits reflecting a light that has traveled 5.5 hours to reach them. Everything here is measured in scales that dwarf human experience. The basin is larger than Hudson Bay. The nitrogen ice beneath you is thicker than most of Greenland's ice sheet. The convection cycle beneath you takes longer than the entire span of recorded human history, multiplied by 400. And yet the science is precise. The measurements are exact. The convection cell diameters of 20 to 40 kilometers imply ice depths of 3 to 6 kilometers by well-established physical models. The surface age of less than 10 million years is calculated from the absence of craters and the rate of bombardment in this region of the solar system. The haze layers at 200 kilometers altitude are measured by the way they attenuated starlight as New Horizons watched stars pass behind Pluto during the flyby. All of this is real. The ground beneath you, the sky above you, the heart that moved the world. You do not need to hold any of it clearly in your mind. You do not need to remember the distances, or the temperatures, or the precise depth of the ice. You only need to know that it is there, all of it exactly as described, exactly as measured, exactly as reported by instruments that traveled for 9 years through the dark to look. It is all there right now, still turning, still breathing. Let that carry you. Let the slow rhythm of this world, the long day, the subliming nitrogen, the rising and falling of ice over 500,000-year cycles, let it pace your breathing, the way this world breathes so slowly that one cycle of its nitrogen makes a human lifetime look like the blink of an eye. You do not need to rush. There is no rush here. The light is soft, the ice is still, the mountains hold their shape. Somewhere beneath you, exactly 4.5 billion kilometers from the room where you are now, warm nitrogen ice is rising toward the surface, just as it has been rising for millions of years, and will continue to rise for millions of years more, long after tonight, long after this voice, long after everything you know is still. You are there, and everything you heard tonight is real. The surface beneath you is not entirely quiet. You cannot feel it, not in the way you would feel movement on Earth. No vibration, no tremor, no sound traveling through the ice into your body. The motion is too slow and too deep for any human sense to register. But the instruments would show it, if you had them. A network of pressure sensors buried in the ice would record, over centuries, the slow differential of rising and falling nitrogen across the plane, the center of each polygon slightly higher than the surrounding troughs. Not by much, a few meters, measured over the full kilometer scale diameter of each cell, but measurably, precisely, continuously rising. The heart of Pluto is not a static thing. It is a process. It has been a process for at least tens of millions of years, and based on what New Horizons measured about Pluto's internal heat budget, there is no reason to expect it to stop. To understand the full extent of what Sputnik Planitia is and does, you need to go farther into it, away from the margins where the water ice mountains crowd the edge of the plain, away from the Ala Drisi blocks and the glacial inflows from the eastern highlands, and into the central expanse where the plain is deepest and the convection most vigorous. You move across the surface. There is no atmosphere worth speaking of at ground level. The pressure is 10 microbars, and even the trace nitrogen vapor drifting above the plain is barely a whisper of gas. But it is there, and it moves. The daily sublimation cycle, nitrogen rising from the sunlit surface of Sputnik Planitia during Pluto's long day, drifting in weak currents driven by the slight thermal gradient between the bright plains and the darker surrounding terrain, and then condensing again as the surface cools, creates real wind. Not the wind you know. Winds here are measured in meters per second, gentle by any planetary standard, but consistent. They have direction, they carry particles, and they make dunes. Near the northwestern margin of Sputnik Planitia, New Horizons imaged a field of transverse dunes, ridges of material oriented perpendicular to the local wind direction, spaced between 400 meters and 1 kilometer apart. The dune particles are thought to be methane ice, approximately 200 to 300 micrometers in diameter, derived from the nearby Ala Drisi Montes. Wind speeds required to move particles of this size on Pluto, given its low gravity, approximately 6% of Earth's, and its extremely thin atmosphere, are calculated at between 1 and 10 meters per second. The dunes exist, the winds are real. They are running right now, carrying methane ice grains across the edge of the world's largest nitrogen glacier in the dim light of a sun that is not much brighter than a star. The dune field is not large by planetary standards, perhaps 30 kilometers across, but its existence is extraordinary. Planetary scientists did not expect to find aeolian features on Pluto. The atmosphere is so thin, the winds so gentle, the particle sizes required for saltation so specific, that dunes seemed impossible before New Horizons arrived. And yet they are there in the data, unambiguous. A transverse dune system with consistent spacing and orientation, preserving in frozen form the direction and approximate speed of the wind that built them. To build a dune on any world, the wind must be strong enough to lift and carry particles, but the relationship between wind speed, particle size, and atmospheric density is complex. On Mars, where the atmosphere is about 1% of Earth's, Dunes are common because the lower gravity reduces the threshold wind speed required to move particles. On Pluto, the gravity is 6% of Earth's, lower than Mars, but the atmosphere is also far thinner, about 1,000 times less dense than Mars's. These two factors partly cancel. The result, according to the models developed after the discovery, is that methane ice particles of the right size can be transported by winds of 1 to 10 meters per second, and those winds, driven by the sublimation cycle of Sputnik Planitia's beating heart, exist. The dunes of Pluto are made of methane ice carried by nitrogen winds. They are transient by geological standards, as Pluto's orbit carries it farther from the Sun over its 248-year year. The nitrogen atmosphere will begin to collapse, the winds will weaken, and the dune field may be buried or dispersed. But right now, at this point in Pluto's orbit, they exist. They are being shaped, they are moving. Everything here is moving. You stand at the edge of these dunes and look out across the plain. The scale of it does not resolve into anything familiar. There are no trees, no buildings, no human-scale objects to anchor your sense of distance. The horizon is closer than Earth's. Pluto's smaller radius means the surface curves away faster, but the plane itself is so vast that its far edge disappears not over the horizon, but simply into haze. The atmospheric haze layers scatter what little sunlight reaches the surface into a diffuse blue-tinged illumination. The ice itself reflects most of that light back upward. The result is a landscape that glows softly from all directions at once, not lit from above, not shadowed below, but simply luminous in a pale, even, directionless way. This is what the end of the solar system looks like: quiet, luminous, alive. In the middle distance, the surface of the plane shows its texture. The polygonal cells are visible as a subtle relief. The slightly raised centers, the slightly depressed troughs between them, creating an irregular grid that stretches to the limits of your vision. Within some of the troughs, where the convecting ice sinks and the material is slightly denser, small dark spots are visible, sublimation pits, where ice has been lost to the atmosphere and the underlying substrate, perhaps water ice, perhaps a thin layer of dark organic tholins, is beginning to show through. And in several places, embedded in the plane itself, you can see what appear to be hills, not mountains, nothing like the Hilary Montes. Small hills, rounded, a few hundred meters high, clustered in loose groups near the margins of convection cells. These are water ice blocks, pieces of the surrounding highland terrain that have calved off and been carried onto the plane by glacial inflow. At Pluto's ambient temperature, water ice is denser than nitrogen ice, which means these blocks should sink, but they do not. The reason is subtle and important. The water ice blocks are porous. They contain trapped gas, nitrogen and methane vapor, within their structure. This reduces their effective density enough that they remain buoyant in the denser nitrogen ice around them, floating at the surface of the glacier the way a slightly porous rock might float at the surface of thick mud. They drift, they cluster. They have been mapped across the plane in patterns that correlate with the convective flow directions, carried by the slow nitrogen currents, corralled into groups where the surface flow converges. The discovery of floating hills on Pluto made scientists reconsider what buoyancy means in a world of multiple ice species. On Earth, the distinction between floating and sinking is simple. Water ice floats on liquid water because solid water is less dense than liquid water, an unusual property that most solids do not share, and one that has profound consequences for the biology of Earth's frozen oceans. On Pluto, the relevant density comparison is between water ice and nitrogen ice. Nitrogen ice at Pluto's surface temperatures has a density of approximately 940 kilograms per cubic meter. Water ice, under those same conditions, comes in slightly lighter, around 920 kilograms per cubic meter. The difference is small, less than 2%, but it is enough. Water ice floats on nitrogen ice, just as water ice floats on liquid water. The physics are the same, only the materials have changed. This means that wherever Pluto's nitrogen glacier meets an outcropping of water ice bedrock, wherever the flow of nitrogen ice carries pieces of the surrounding terrain onto the plain, those pieces will rise. They cannot sink. The nitrogen beneath them is just dense enough to push them up, and they drift at the surface, carried by the convective currents, clustering where the flow converges, dispersing where it spreads. The hills you are sitting on have been drifting for a long time, possibly since the nitrogen ice first rose high enough in Sputnik Planitia to carry them off the basement bedrock, possibly since some collapse event at the basin margin sent a mass of water ice blocks tumbling onto the plain. The exact history of this particular cluster is unknown. New Horizons passed once, and its cameras recorded a snapshot, not a movie. But the physics is clear, and the physics says these hills are not fixed. They are passengers. Floating hills carried by a glacier of frozen air. You sit on one of these hills. It rises perhaps 150 meters above the plain. From this elevation, the full extent of Sputnik Planitia is more apparent, the white expanse stretching in every direction, broken only by the distant dark rims of the surrounding highlands and the subtle polygon texture of the surface below. The silence here is total. There is no wind at this moment. The sublimation cycle is in its quiet phase. The sunlit hemisphere has rotated away, and the surface is cooling, nitrogen vapor condensing back as a thin, fresh layer of frost. The rate of this deposition is tiny, a fraction of a millimeter per day, but over the course of millions of years, compounded and cycled and redeposited, it is enough to maintain the glacier's thickness, to keep the plain fresh, to keep the surface age measured in tens of thousands of years rather than billions. Let the silence hold. The nitrogen beneath you is completing the bottom half of its convective turn. Somewhere 3 to 4 kilometers below the surface you are sitting on, material that was once at the top of a convection cell that cooled and sank along the edges of its polygon is now approaching the base of the nitrogen layer, where it will be rewarmed by the faint heat rising from Pluto's rocky core. It will begin its slow ascent again. It will take another 250,000 years to reach the surface. You will not be there to see it. But the process will not pause for your absence. It does not require observation. It does not require any awareness at all. It simply continues, the arithmetic of heat and density and gravity resolving itself in the dark and the cold, as it has been resolving since the nitrogen first pooled in this basin, before any creature on Earth had learned to count. Farther south, past the edge of Sputnik Planitia, the terrain changes. The boundary between the nitrogen plain and the surrounding highlands is not always clean. In some areas, the plain terminates sharply against a wall of older, cratered terrain. In other areas, the transition is gradual. The nitrogen ice of the plain thins and gives way to a mixed zone, where nitrogen ice and water ice bedrock are both present, where the surface is neither the uniform white of the glacier, nor the darker tan of the uplands, but something in between. It is in this transitional zone, and in the highlands immediately beyond it that the glacier system becomes even more complex. To the east and northeast of Sputnik Planitia, a network of valleys descends from the surrounding uplands toward the plain. These valleys are carved, not by liquid water, not by any process familiar from Earth's temperate geology, but by glacial flow. Nitrogen ice accumulates in the upland highlands through atmospheric deposition. Nitrogen vapor, transported by the weak winds of Pluto's sublimation cycle, settles and freezes in the higher latitude pockets of the eastern terrain. When enough accumulates, it flows downhill, slowly, through whatever topographic channels exist, into Sputnik Planitia. These glaciers are unlike anything on Earth. On Earth, a water ice glacier moves under the influence of its own weight, deforming the ice at its base and sliding over bedrock. The meltwater at the base of Earth's glaciers lubricates the contact and allows movement. On Pluto, there is no meltwater. The temperatures are far too low for any liquid nitrogen to exist at the base of the glacier. Instead, the nitrogen ice deforms entirely through solid-state creep. The crystal structure of the ice slowly rearranges at the microscopic level in response to stress, allowing the bulk material to flow without any actual melting. And here is the counterintuitive reversal. On a water-ice glacier on Earth, if you were to imagine the ice melting at the base, that melt would flow downward, away from the glacier. On Pluto, if nitrogen ice were to melt anywhere within the glacier, due to some unusual concentration of heat, the resulting liquid nitrogen would be less dense than the surrounding solid nitrogen. It would rise, it would make its way to the top of the glacier, and there, at the surface, where pressure is lowest, it would flash to vapor and potentially erupt, not violently, but as a gentle transient jet or geyser of nitrogen gas. This is not confirmed to have occurred on Pluto, but the physics permits it. Triton, Neptune's largest moon, captured from the Kuiper Belt and therefore closely related to Pluto in composition, has confirmed nitrogen geysers on its surface, driven by solar heating of transparent nitrogen ice that allows sunlight to warm a dark substrate below. Pluto's nitrogen ice behaves differently, but the family resemblance is there. You walk along the edge of one of these eastern glacier inflows. The valley walls are water ice bedrock, their surfaces stained the muted orange tan of accumulated tholins. The floor of the valley is nitrogen ice, smooth and white, flowing almost imperceptibly toward the plain. The walls rise perhaps 2 kilometers on either side. The scale is that of a major alpine valley on Earth, the kind of valley carved over millions of years by glacial advance and retreat. But on Pluto, there was no warm interglacial period that created this topography. The valley walls are old, cratered terrain. The glacier filling the valley floor is geologically young. Ancient walls, young ice, the same landscape, 2 different timescales occupying the same space. You look down the valley towards Sputnik Planitia. The glacier's surface carries faint lineations, streaks in the ice, oriented along the direction of flow, formed by differential velocity across the width of the glacier. The center moves slightly faster than the edges, where friction with the valley walls slows the flow. These lineations are subtle from the surface, but visible in the New Horizons imagery from above. They are the fingerprints of flow, the record of movement written in the texture of the ice itself. Everything on this world writes its history in ice. In, hold, out. You follow the glacier down to where it meets the plain, and you step back onto Sputnik Planitia, From here, looking south and west, the terrain beyond the plain begins to reveal itself, the highlands that border the glacier on its southern and western margins, and within those highlands, something that has no clear parallel anywhere else in the solar system that we have yet explored. Two mountains. Not the water ice mountains of Hilary Montes or Tenzing Montes, which rise steeply from the edge of the glacier and are composed of the same ancient water ice bedrock that underlies most of Pluto's crust. These are different. These mountains are rounded, gentle in their slopes, enormous in their diameter, and they each have something that the water ice mountains of the glacier margin do not. A central pit. Right Mons lies to the southwest of Sputnik Planitia at approximately 23 degrees south latitude. Its base diameter is approximately 150 kilometers. Its summit rises 4 to 5 kilometers above the surrounding terrain. At its center is a depression approximately 45 kilometers wide and 4 kilometers deep, a pit that descends into the mountain's interior rather than being a simple impact crater. The pit's walls are steep, and the terrain surrounding it is hummocky, irregular, lumpy, without the smooth layering of impact ejecta. Scientists examining this morphology in the New Horizons imagery concluded that Right Mons most likely formed not through impact but through internal volcanic processes. Picard Mons, farther south, is larger, a base diameter approaching 250 kilometers, an even more pronounced central pit, and the same hummocky surface texture. It is, if confirmed as volcanic, the largest volcano yet identified in the outer solar system. Neither of these mountains is made of the silicate rock that forms volcanoes on Earth or the Moon. The temperatures on Pluto are too low and the internal heat too limited to mobilize rock. What flows from these mountains, if anything is still flowing, if anything has flowed in geologically recent time, is ice. But not the nitrogen ice of the glacier, not the methane ice of the bladed terrain. Water ice? At first this seems wrong. Water ice is rigid and structural at Pluto's surface temperatures, as hard and immobile as granite. How could it erupt? The answer is that it almost certainly does not erupt pure. Pluto's interior, beneath the water ice crust, likely contains materials that lower the melting point of the water ice: ammonia, methanol, antifreeze-like compounds that can keep a water-ammonia mixture liquid at temperatures far below water's normal freezing point. A mixture of roughly 30% ammonia in water remains liquid down to approximately 176 degrees below 0 Celsius. This is still far colder than anything on Earth, but it is warmer than Pluto's surface. And the evidence for this mixture is direct. In the Virgil Fosse region, to the west of Sputnik Planitia, New Horizons detected ammonia on the surface in spectroscopic data, specifically in the walls of the Cosmata, the long fractures and troughs that cut across this region of Viking Terra. The ammonia signature is fresh. It has not been processed by ultraviolet radiation or cosmic rays, which would chemically alter it over timescales of tens of millions of years. If the ammonia is fresh on the surface, it was recently emplaced. The most recent estimate from the scientific literature, the ammonia-rich cryolavas in the Virgil Fosse region were emplaced no more than 1 billion years ago, and possibly far more recently than that. In an area of several thousand square kilometers, red-colored organic material, tholins, coats the surface in a pattern consistent with a fluid having erupted from the fractures and spread across the surrounding terrain. A cryovolcanic eruption on Pluto within the last billion years. In cosmic terms, that is not long ago. Something came up through the ice, something warm, something that left a mark. You are standing in the Virgil Fosse region now. Imagine it. The ground beneath you is fractured. Long, parallel troughs cut through the water-ice bedrock, some of them kilometers wide and several hundred meters deep. The walls of these troughs are layered, dark tholins on the surface, white water ice showing where the tholins have been eroded, or where the fracture cut through the ice cleanly. In some areas along the floors of the troughs and spreading outward across the adjacent terrain, a reddish material coats everything, the organic compounds deposited when ammonia-rich slush erupted from below and spread across the surface, and then froze, and then was slowly processed by ultraviolet radiation and cosmic rays into the complex molecular tangles that give tholins their color. The ammonia came from below, from somewhere in Pluto's interior where the water ice crust is thin enough, or the internal heat concentrated enough to have maintained a pocket of liquid ammonia-water mixture. The fractures provided the pathway. The pressure from below provided the driving force. The mixture rose through the fractures, emerged at the surface, spread, and froze almost instantly in the -200-degree air. The surface record of this event is a few thousand square kilometers of reddish organic coating, long fractures in the ice, and the ammonia spectral signature that New Horizons detected as it flew past. The internal record is hidden. Whatever drove the eruption, whatever thermal anomaly or pressurized pocket, produced enough force to push a slurry of water and ammonia through kilometers of ice, is below you now, invisible, possibly still warm, possibly still pressurized, possibly still capable of erupting again. You do not know if it is finished. Nobody does. Let that settle into the quiet of this world, not as fear. There is nothing threatening in this for you, nothing urgent, nothing that requires action or decision, only the recognition that the interior of Pluto is not fully understood, that the models of its thermal history are being revised as new analyses of the New Horizons data emerge, that a world so small, so cold, so far from the sun, maintains enough internal complexity to produce geologically recent volcanic events, even cold volcanic events, even ice slurry eruptions, challenges every assumption about where the threshold of planetary activity lies. The working model of Pluto's interior looks like this. At the center, a rocky core approximately 1,700 kilometers in diameter, rock and silicate material, compacted under Pluto's own gravity, still generating heat through the radioactive decay of long-lived isotopes, uranium-238, thorium-232, potassium-40. The heat output is low, far lower than Earth's rocky interior, but it has been running continuously for 4.5 billion years, and it is still running now. Around the core, a shell of water ice approximately 300 kilometers thick, but not entirely frozen. Based on the geological evidence from New Horizons, the extensional faulting patterns observed across Pluto's surface, which indicate that the crust has been slowly expanding rather than contracting, and the tectonic structures that point to an ancient period of rapid early extension, the models suggest that a layer of liquid water may exist at the base of this ice shell, pressed against the top of the rocky core, an ocean, not exposed to the surface, not accessible, not frozen because the pressure at that depth lowers the freezing point of water, and because the heat from the core is sufficient, barely, to keep it liquid. This subsurface ocean may be tens to hundreds of kilometers thick. It is probably very salty. It may contain dissolved ammonia. It is in complete permanent darkness. It has never in 4.5 billion years been touched by sunlight. And yet it exists. Above the ocean, the water ice shell continues upward to the surface, perhaps insulated in part by a layer of methane clathrate, a cage-like crystalline structure in which water ice molecules surround trapped methane gas. This clathrate layer, if it exists, would have a thermal conductivity approximately 5 to 10 times lower than ordinary water ice, acting as an insulating blanket that slows the escape of heat from below and helps maintain the liquid ocean against the freezing cold of the deep outer solar system. The nitrogen ice of Sputnik Planitia sits on top of all of this, like a bright white cap over an ice shell over a hidden sea. Charon also shows evidence of its own internal history in the fractures that cut across its surface. The Serenity Chasma, a system of chasms that girdles Charon's equatorial region, stretches for at least 1,000 kilometers and reaches depths of up to 9 kilometers. Arrokoth, one of the largest individual features in this system, has cliff walls that may rival Verona Rupes on Miranda for the title of the tallest cliff in the solar system. These fractures are extensional. They formed when Charon's crust was being stretched apart from below, indicating that Charon, like Pluto, went through a phase of internal expansion. The most likely cause, a subsurface ocean freezing. As water freezes, it expands by approximately 9%. A freezing ocean inside Charon would have pushed outward on the overlying crust, stretching and fracturing it. Charon's ocean, unlike Pluto's, is believed to have fully frozen billions of years ago. Charon is smaller, has less rock, and less radioactive material to generate internal heat, and is farther from any tidal heating source. Its ocean formed, expanded as it froze, cracked the crust, and then solidified completely. The extensional fractures are the record of its freezing, a wound left by a vanished sea. The South Pole of Charon tells a different story than the North, where the North Pole is red with tholins captured from Pluto's atmosphere. The South Pole is covered with something simpler, bright water frost, deposited during Charon's decades-long southern winter when the pole is in permanent darkness and cold enough to trap any trace gases that drift by. The contrast between the two poles, one red with organic complexity, one white with simple frost, maps the asymmetry of Charon's position relative to both Pluto and the Sun. Charon faces Pluto on one side. On the other side, it faces open space. The face toward Pluto catches more atmospheric escape products. The face away from Pluto receives less. The surface composition of Charon's two hemispheres differs in ways that directly reflect this geometry, mapped by New Horizons in color images that revealed subtle but measurable differences in the Tholen distribution across the Moon's surface. Two worlds, locked face to face, painting each other slowly across billions of years. You think about what it would mean for that ocean to be there. Not in astrobiological terms, not the hopeful speculation about whether life could survive in a dark, cold, ammonia-laced ocean at the edge of the solar system, simply in terms of what it means for our understanding of where liquid water can persist in the universe. Before the Voyager missions, before Galileo at Europa, before Cassini at Enceladus, before New Horizons at Pluto, the operating assumption was simple. Liquid water requires proximity to a star. The habitable zone, the narrow band of orbital distances around a star where the surface temperature is right for liquid water, was considered the boundary condition for everything interesting. Beyond that zone, everything was frozen and dead and static. That assumption has not survived contact with the outer solar system. Europa has an ocean, Ganymede has an ocean, Enceladus has an ocean and is actively venting liquid water into space through its southern polar geysers. Titan has a subsurface ocean and liquid hydrocarbon lakes on its surface. And now Pluto, at 39 astronomical units, more than 1 billion kilometers beyond the traditional outer edge of any habitable zone, may have an ocean too. The ocean on Pluto, if it exists, is maintained not by sunlight, but by the slow decay of radioactive elements in its core. It has nothing to do with the sun. It is self-contained, independent, a pocket of liquid water in the dark, kept warm by the same physics that keeps Earth's interior warm, just operating at a much smaller scale, on a much smaller body, in a much colder neighborhood. This world has a companion. Everything you have seen tonight, the nitrogen glacier, the floating hills, the cryovolcanic fields, the possible subsurface ocean, all of it exists in gravitational partnership with a body nearly half its own size. Charon, the largest moon relative to its host planet of anything in the solar system except, by some measures, Earth and its own moon. But the Earth-Moon relationship is not the same as the Pluto-Charon relationship, because Pluto and Charon are mutually tidally locked. Both bodies keep the same face toward each other, always. The Earth rotates freely, oblivious to the moon's fixed gaze. Pluto and Charon do not rotate independently of each other at all. They are locked in a permanent mutual face, orbiting their common center of gravity, a point that lies not inside Pluto, but outside it, in the space between the two bodies, with a period of 6.4 Earth days. This is unusual. Most moons orbit their planets from a position of relative insignificance. Their gravitational influence is modest, their effect on the planet's rotation minimal. Charon is 12% of Pluto's mass. Its gravitational pull on Pluto is substantial. It was Charon's gravity, working in combination with the massive imbalance introduced by Sputnik Planitia's nitrogen ice, that completed Pluto's polar wander, that locked the heart in its current position and held it there. Charon did not merely accompany Pluto. Charon shaped it. And Charon itself is a world worth examining. Its diameter is 1,212 kilometers, larger than the dwarf planet Ceres, larger than any moon of Uranus. Its surface gravity is approximately 33% lower than Pluto's, meaning it is even smaller and less massive, but it is still large enough to be spherical, large enough to have differentiated into a layered interior, large enough to have its own geological history. And what a history! The surface of Charon, as New Horizons photographed it, is divided sharply into two distinct regions. The southern and equatorial areas are heavily cratered, ancient terrain, pale gray water ice, billions of years old, recording the accumulated impacts of 4 billion years in the Kuiper Belt. But the North Polar region is something else entirely. A large, dark reddish cap, informally named Mordor Macula, covers Charon's North Pole in a material whose color is unmistakably the color of tholins. But Charon has no significant atmosphere. It cannot produce tholins internally the way Pluto does, through photochemical reactions in a nitrogen-methane gas mixture. So where did the tholins come from? The answer is Pluto. Pluto's tenuous atmosphere extends upward from the planet's surface in a long, expanding envelope. The atmospheric escape rate, the rate at which gas molecules moving at the high end of the thermal velocity distribution exceed Pluto's escape velocity and leave the atmosphere entirely, is not enormous, but it is measurable. New Horizons detected this escaping atmospheric material directly. Some of this escaping nitrogen and methane drifts through space and encounters Charon. Charon's much lower escape velocity means it cannot hold on to any gas at normal temperatures. But in Charon's polar winter, which, due to Pluto's extreme axial tilt of approximately 51 degrees, can last for decades, the polar regions grow cold enough to trap even trace amounts of nitrogen and methane as frost. This frost accumulates over the winter. When Charon's polar summer arrives, most of the frost sublimes back to space, but some of the methane, before it can escape, is chemically processed by ultraviolet radiation from the sun and cosmic rays, converted into tholins, the same reddish organic compounds that color Pluto's surface in haze. The tholins do not sublime easily. They remain on the surface after the nitrogen and methane have gone. Over billions of years, this process has painted Charon's North Pole red with Pluto's atmospheric exhaust. The moon wears the remnants of its companion's breath. This changes something fundamental in how we think about where oceans can be, not just in our solar system, but in any planetary system around any star, anywhere in the galaxy. If a world the size of Pluto, small enough to fit between New York and London if you laid it flat, can maintain a subsurface ocean through radioactive heating alone, then subsurface oceans may be extraordinarily common in the universe. Not on the surfaces of planets, not in the sunlit, warm, obvious places we have always looked, but below the ice, in the dark, powered by physics that has nothing to do with starlight. Consider what that ocean would be like if you could somehow reach it. You would need to descend through the nitrogen ice of Sputnik Planitia, 4 kilometers, perhaps more, at the center of the basin. Below that, the bedrock of water ice, old and dark and compressed. Down through perhaps 200 kilometers of water ice, the pressure increasing with every kilometer, the temperature slowly rising as the heat from the core accumulates. And then, at some depth, the models disagree on exactly where the ice would give way. Not dramatically, not in a cavern or an open sea in the way that science fiction imagines subterranean oceans. More likely a gradual transition. First ice that is warm enough to be slightly plastic, slightly mobile at the smallest scales, then ice laced with pockets of brine, water so concentrated with dissolved salts and ammonia that it remains liquid even at temperatures well below the normal freezing point. And finally, deeper still, something that is unambiguously liquid. The water in that ocean would be unlike any water you have touched. Its temperature might be close to 0 Celsius at the top, the warmest the bottom of the ice shell gets, and perhaps slightly warmer closer to the rocky core. But the pressure at that depth, under 200 kilometers of ice, would be enormous, approximately 20,000 atmospheres. Under this pressure, water ice adopts unusual crystalline structures, high-pressure ice phases with names like Ice 6 and Ice 7 that are denser than liquid water and would form at the base of the ocean rather than floating on it. Unlike ordinary ice, the ocean would be bounded above by ordinary ice and below by high-pressure ice. It would be utterly lightless. No photon from any star has ever reached those depths, or ever could. Whatever chemistry is occurring in that ocean occurs in permanent, absolute darkness. Whether any chemistry is occurring, whether the conditions permit any kind of complex molecular organization, any self-sustaining reaction system, any analog to what we call life, is genuinely unknown. The ocean exists if it exists, too far away and too deeply buried for any current technology to investigate directly. New Horizons flew past in 2015 and gave us 9 days of flyby data. As of today, no follow-up mission has been funded, built, or launched. The ocean under Pluto may remain inaccessible for decades or longer. But it is there, in the models, in the data, in the tectonic patterns that New Horizons imaged, and that thermal physicists have spent years trying to reproduce computationally. The extensional fractures on Pluto's surface, the long, normal faults that indicate the crust has been expanding outward, are consistent with a world whose interior was once warmer and has been slowly cooling and freezing outward, releasing the pressure of a contracting liquid interior as ice and causing the crust to fracture and spread. The amount of extension observed, approximately 0.5% of linear strain over the last 3.5 billion years, matches the models for a Pluto with a subsurface ocean that is slowly but steadily freezing at its base. The ocean is shrinking, millimeter by millimeter, year by year, across geological time. The cold is winning, but it has not yet won. And in the timescales relevant to us, human lifetimes, human civilizations, even human species, it will not win. The ocean, if it is there tonight, 4.7 billion kilometers from where you are now. In the dark, warm, liquid. Patient? This is not speculation. It is the straightforward implication of what the thermal models, the geological observations from New Horizons, and the measured properties of Pluto's interior all point toward. The ocean may be there, and if it is, it has been there for billions of years. The surface above it is ancient and cold and quiet. Beneath you, perhaps, it is liquid and dark and permanent. You lie back on the nitrogen ice and look up. The sky above Sputnik Planitia is not completely dark. The haze layers scatter and redirect what little sunlight arrives, producing a diffuse glow at the edges of vision, the blue atmospheric limb that New Horizons photographed in its backlit departure image, reproduced now in your imagination exactly as the data recorded it. 20 distinct haze layers, each a thin stratum of tholins at a slightly different altitude, together producing a ghostly luminescence in the upper atmosphere. The stars are visible through the haze, more stars than you have ever seen from Earth. The haze is thin enough to be nearly transparent, and there is no moon-scale reflected light to wash out the fainter objects. The Milky Way is a visible band, slightly brighter than from Earth's dark sky sites, the galactic plane stretching in a clean arc across the black. The sun is a brilliant point, unmistakably the brightest object in the sky, but not warm, not comfortable, not the sun you know. And somewhere in that sky, a pale blue dot. Earth is not visible to the naked eye from Pluto. At this distance, approximately 32 astronomical units, when New Horizons made its flyby, Earth and the Sun are so close together in angular terms that the two cannot be separated without a telescope. But if you could see it, Earth would be a point of light, blue and infinitesimal, indistinguishable from the other stars, except by the subtle color of its reflected sunlight. Your entire history, every human being who ever lived, every city, every ocean, every mountain range, every war and birth and harvest, all of it contained in a point of light that a telescope would be required to find. The nitrogen ice beneath you continues its slow turn. The tholins above continue their slow settling. And somewhere in this world, In the dark interior that no spacecraft has ever reached and no instrument has ever directly measured, the rocky core is releasing heat. The ice above it is pressing against the boundary between solid and liquid, and the ocean, if it is there, is lapping silently against the underside of the frozen shell. You will not hear it. It is kilometers below you. It is water so cold and pressurized that it barely resembles the water you know. But if the models are right, if the thermal calculations hold, and the geological evidence is interpreted correctly, it is there. Right now, tonight, 4,700 million kilometers from where you are actually lying. A hidden ocean under a nitrogen glacier, under a blue haze, under a sky full of stars. You let your breathing slow. The vast polygons of Sputnik Planitia turn their slow half-million-year cycles below you. The bladed methane terrain of Tartarus Dorsa stands in its ordered rows to the east, unchanged from the moment New Horizons photographed it, unchanged tonight, unchanged for 1,000 human lifetimes in either direction. The cryovolcanic fields of Virgil Fosse lie quiet to the west, their reddish organic coating undisturbed. And beyond the southwestern edge of Sputnik Planitia, past the Hillary and Tenzing Montes, Right Mons rises in the dark, enormous, rounded, its central pit open to the sky, quiet now, whatever drove it now still, whatever will drive it next, still waiting in the interior. Something is still in there. You do not know what it is about to do. Nobody does. The plains are still, the ice is still, and somewhere very far above you, in the thin blue haze of a world at the edge of everything, the tholins are falling. But there is something above you too. Not just the haze, not just the tholins falling through 20 strata of thin atmosphere. Above all of that, above the nitrogen that Pluto's faint gravity can barely hold, above the methane and the acetylene and the ethylene drifting in the upper exosphere, there are 4 small moons. Not Charon, you already know Charon. Charon is fixed in the sky from this side of Pluto, neither rising nor setting, locked in its mutual gaze, its dark Mordor cap facing you like a bruise. The 4 moons are different. They are small, irregular, tumbling, and they do not orbit in the calm, stately way that most moons orbit their planets. They spin. Nix, Hydra, Styx, and Kerberos, the 4 small moons of Pluto, rotate far faster than their orbital periods. Nix completes a full rotation in approximately 43 hours, while taking 24 Earth days to complete one orbit. Hydra spins even faster, one rotation in approximately 10 hours. This rapid, chaotic spin is not an accident. It is the direct consequence of the Pluto-Charon binary's gravitational influence. The tidal environment of a binary system, 2 large bodies orbiting a common center, is far more complex and variable than the environment around a single planet. The torques imposed on small satellites by the changing gravitational field, created by Pluto and Charon, rotating around each other, are irregular and unpredictable over long timescales. The result is chaotic rotation. The small moons tumble without settling into any stable orientation. From the surface of Pluto, if you had a telescope, you would see Nix and Hydra as distinct points of light, not stars, because they move measurably against the star background over hours, and because their brightness varies as their irregular shapes present different cross-sections to the sun. Styx and Kerberos are fainter. Styx is one of the smallest known moons in the solar system, with a longest dimension of approximately 16 kilometers, and its surface is bright with water ice that reflects sunlight efficiently but offers very little surface area to reflect from. These 4 moons are thought to have formed from the same collision event that created Charon, when Proto-Pluto and Proto-Charon collided 4.5 billion years ago, when the 2 worlds briefly merged into a snowman-shaped body, rotating together for 10 hours before Pluto pushed Charon outward into its current orbit. The collision and separation process left debris in the surrounding space. Small fragments of rock and ice ejected from the surfaces of both bodies during the violent contact phase settled into orbits around the newly formed binary. Over time, these fragments accreted into the 4 small moons. They are, in a sense, chips off the collision, remnants of the moment Pluto found its companion. 4 small worlds, tumbling, ancient, shaped by a collision 4.5 billion years ago, still tumbling now, tonight. The Pluto system, the dwarf planet, its 5 moons, its nitrogen glacier, its possible ocean, its cryovolcanic fields, its bladed methane terrain, all of it formed from a single catastrophic event in the early Kuiper Belt, and all of it has been evolving, differentiating, changing, and in some cases actively renewing itself ever since. This is important not just for understanding Pluto, it is important for understanding the Kuiper Belt as a whole. The Kuiper Belt holds objects larger than 100 kilometers in the hundreds of thousands, with smaller bodies numbering in the hundreds of millions to trillions. Of the 10 largest Kuiper Belt objects, 8 are known to have large moons. The inference is significant. Large collisions, not captures, not gentle accretion, but genuine high velocity or moderate velocity impacts between sizable icy worlds were common in the early outer solar system. The Kuiper Belt was not always the quiet, cold, sparsely populated debris field it is today. In the first few 100 million years of the solar system, when the giant planets were migrating into their current orbits, the Kuiper Belt was stirred. Objects that had been orbiting at stable, quiet distances were perturbed into crossing paths. Collisions happened. Pluto's 5-body system is one of the surviving outcomes of that era of violence. In Pluto itself, the geological complexity, the active nitrogen glacier, the possible subsurface ocean, the cryovolcanic activity, is the product not just of its formation collision, but of the entire 4.5 billion years of evolution that followed. The radioactive elements in its core have been generating heat since before the Earth had fully formed. The subsurface ocean, if present, has been liquid since the solar system was young. The nitrogen that forms Sputnik Planitia has been cycling between vapor and ice and vapor, for longer than any life on Earth has existed. Pluto is not a remnant. It is not a frozen leftover. It is an evolved world, one that has been processing, differentiating, and renewing itself across the full span of solar system history, in conditions so extreme that we are still working out the details of how any of it is possible. Arrokoth taught scientists something that Pluto had hinted at but could not confirm on its own. Before Arrokoth, the leading model for how planetesimals, the building blocks of planets and moons, formed in the early solar system, was hierarchical accretion, small particles clumping into larger ones through repeated low-velocity collisions, gradually building up to the 100-kilometer scale over millions of years. The problem with this model was always the intermediate stage, particles large enough to be affected by gas drag, but small enough to drift rapidly toward the sun, tend to be destroyed or lost before they can accumulate into planetesimals. There was a size gap in the theory. Arrokoth changed that. Its shape, two lobes, each individually round, gently pressed together in a contact binary, tells a specific story. The lobes did not collide violently, they formed nearby, orbiting each other in the same region of the Kuiper Belt, accreting from the same local cloud of pebbles and dust, in a process called pebble cloud collapse. When enough material had gathered, gravity pulled the two lobes together in a slow, gentle approach, and they touched at a relative speed of perhaps a few meters per second, barely a walking pace. No fracturing, no melting, just a gentle contact and a mutual settling. This is how much of the outer solar system likely formed, not through catastrophic high-speed impacts, but through slow, cold, gentle accumulation, pebble clouds collapsing under their own gravity, forming binaries merging, the whole process operating in slow motion in the frigid outer disk of the young solar system before the giant planets had fully migrated to their current positions and stirred everything into the more chaotic environment that created Pluto's formation collision. Pluto and Arrokoth are both products of the Kuiper Belt, but of different eras and different processes. Arrokoth is the quiet beginning. Pluto is what happens after billions of years of evolution. Both are necessary to understand where all of this came from. The full picture of the outer solar system is still being assembled. Every dataset from New Horizons, still being analyzed in 2026, adds a piece. Every paper that emerges from the archive of flyby observations revises the models slightly. The planet that Clyde Tombaugh found by blinking photographic plates in 1930, the tiny flickering point that looked like nothing, has turned out to require entire fields of planetary science to describe. Hydrology on an airless world, glaciology at 38 Kelvin, volcanology with water and ammonia instead of basalt and silica, oceanography under 200 kilometers of ice. These are not metaphors, they are the actual scientific disciplines that Pluto has opened. In, hold, out. Now think about what New Horizons is doing tonight. The spacecraft that gave us all of this, the piano-sized probe with its 7 instruments and its 1 kilobit per second radio link, and the ashes of Clyde Tombaugh in a small container attached to its interior, did not stop at Pluto. It could not. A flyby by definition does not stop. New Horizons crossed the entire Pluto system in hours, recorded everything it could, and continued outward. On January 1st, 2019, 3.5 years after the Pluto flyby, New Horizons reached its next target, a small Kuiper Belt object called Arrokoth, 4 billion miles from Earth, at the time the most distant object ever explored, up close by a spacecraft. Arrokoth is a contact binary, 2 lobes of reddish ice and rock gently fused together into a shape scientists compared to a snowman. Each lobe formed independently in the early Kuiper Belt, not through violent collision, but through gentle, slow-motion accretion, pebble by pebble, in the same neighborhood, orbiting each other in a gradually tightening spiral until they touched and held. Arrokoth is the most primitive object ever examined by a spacecraft. It has been sitting largely undisturbed in the outer Kuiper Belt for 4.5 billion years. It is, in the truest sense, a piece of the beginning. As of October 2024, New Horizons passed 60 astronomical units from the Sun, twice as far as Pluto was during the flyby. It is now in the Kuiper Belt's outer reaches, where the density of objects begins to thin toward the vast emptiness of interstellar space. Its instruments are still functioning, it is still transmitting, it is measuring the particle environment, the magnetic field, the ultraviolet light from distant sources, building a profile of a region of space no human instrument has ever sampled in situ. The data it returns takes more than 8 hours to arrive. The team that launched it in 2006 is older now. Some of them have retired. New Horizons itself has been extended twice beyond its original mission, first to the Kuiper Belt extended mission through the Arrokoth flyby, then extended again as it continues its measurements from the deep outer solar system. It is expected to operate until the mid-2030s before its power supply drops too low to run its instruments. After that, it will continue, silent and dark, still moving outward at roughly 14 kilometers per second. It will cross into the space between the Kuiper Belt and the Oort cloud, a vast, largely empty region spanning tens of thousands of astronomical units, and eventually, in the far future, it will cross into interstellar space, as Voyager 1 and 2 did before it. New Horizons will never return. No spacecraft has ever returned from the outer solar system. They go out and they keep going, slowing imperceptibly under the sun's gravity but never stopping. Voyager 1, launched in 1977, is now more than 230 astronomical units from the sun and still moving. It will be tens of thousands of years before it makes a close approach to another star. New Horizons, launched in 2006, is on a similar trajectory, outward, always outward, into the dark between stars. Out there tonight, moving, everything it knows about Pluto, already in its memory banks, already sent home. The knowledge it returned changed what we know about the outer solar system irrevocably. Before 2015, Pluto was a fuzzy dot with a large moon and a thin atmosphere. After 2015, it was one of the most geologically complex worlds ever examined, a world with a beating heart, possible cryovolcanoes, evidence for a subsurface ocean, a dynamic atmosphere, active glaciation, dunes, floating mountains, and a moon whose north pole had been painted red by the planet it orbits. All of this from a single flyby. 9 days of data, 16 months of transmission at 1 kilobit per second. The complete dataset from the Pluto flyby, more than 50 total gigabits, was received in full on October 25th, 2016. Scientists are still analyzing it. New papers continue to appear in the peer-reviewed literature. The 2022 Nature Communications paper on large-scale cryovolcanic resurfacing was published 7 years after the flyby. The 2025 paper reanalyzing Charon's formation scenario appeared a full decade after the closest approach. The dataset from 9 days in 2015 is still yielding discoveries in 2026. There is more to find. There is always more to find. You look up from the surface of Sputnik Planitia, from the place you have been lying on this slow, luminous glacier, and you look in the direction the spacecraft went. Not toward the sun, away from it, outward, into the black beyond the Kuiper Belt, beyond Arrokoth, beyond everything we have mapped and named and visited. New Horizons is out there, still moving, still alive for now. A piano-sized object traveling at 14 kilometers per second through a region of space so empty that the nearest atom is, on average, more than a cubic centimeter away from the last. It carries the name of the mission that finally gave Pluto its face. It carries Clyde Tombaugh's ashes, the man who spent months staring at photographic plates in Flagstaff, Arizona in 1930 until a single point of light flickered in the wrong direction against the stars. It carries the names of nearly 500,000 people who wanted to send something of themselves to the edge of the solar system. In some sense, it carries everything the story has given you tonight. The understanding that distance is not emptiness, that cold is not death, that a world can be geologically active and atmospherically dynamic and internally complex at 39 astronomical units from the sun, in the dark and the cold, on no energy source except the patient decay of ancient atoms and the faint angular warmth of a star that looks from there like a very bright point. The Kuiper Belt stretches out in every direction around you. Hundreds of thousands of icy worlds, most of them never visited, most of them probably never to be visited in any time frame that matters to human civilization. Each one is different. Each one has its own interior, its own surface chemistry, its own history of collisions and accretion and thermal evolution. Pluto is the largest and the most studied, but it is one example among hundreds of thousands. Some of those other worlds may have their own nitrogen glaciers, their own subsurface oceans, their own slow geological processes, running quietly in the dark, unknown to anyone. We have been to one. Just one. Let your breathing settle into the pace of this place. Not the pace of a city, or a conversation, or a task list. The pace of nitrogen ice rising 3 kilometers over 500,000 years. The pace of tholins settling through 20 haze layers onto a surface that will not see a spacecraft again for decades, possibly longer. The pace of a world that does not know it is being observed. That has never needed to know. The sun is a bright star to the southwest. Charon hangs motionless above the opposite horizon, its dark Mordor macula facing you across the 150 kilometers of mean orbital radius that separates the two bodies, the two worlds that touched for 10 hours and have been circling each other ever since, locked in a gravitational conversation that will continue for billions of years more. The nitrogen beneath you is rising, slowly, in cells 20 to 40 kilometers across, warm material climbing through 4 kilometers of ice toward the surface, where it will cool and sink and begin the cycle again. The haze above you is settling, slowly, fallen particles drifting downward through 20 strata, each stratum a slightly different altitude, slightly different particle size, slightly different optical depth, together producing that faint blue luminescence at the edges of the world. The heart is breathing in and out, nitrogen subliming in the Plutonian day, condensing in the Plutonian night, driving the weak circulation that makes Sputnik Planitia not just a glacier but a climate engine, the engine that moves the planet's air such as it is from one hemisphere to another and back again in a rhythm that repeats every 6.4 Earth days. Every 6.4 Earth days, the heart of Pluto completes one breath. You do not need to match that rhythm. You are already slowing to something gentler, something closer to your own natural pace. The words can carry less weight now. The science has been given, the distances, the temperatures, the convection cells, the cryovolcanoes, the ocean, the moons. It is all real. It has all been measured. It is all happening right now as you listen in a place so far away that the signal confirming its existence takes more than 5 hours to arrive, even at the speed of light. And yet it is not distant in the way that matters. It is here in the same way that a story is here, present in the mind that holds it, real in the imagination that gives it space, permanent in the way that understanding always is. You will not remember all of it. You do not need to. What stays is what always stays. The scale, the surprise, the recognition that the universe is far stranger and far more alive than it appears from where you stand. Pluto is strange. Pluto is alive. Pluto has a heart that moved a planet, mountains that float on frozen air, a moon painted red by its own companion's breath, and somewhere beneath it all, in the dark under the ice, possibly water, liquid, warm, patient. If you are still awake, this is the part where the words begin to thin. Not because the story is over. The story is not over. Scientists are still reading New Horizons data. New papers will be published. New analyses will revise the models. The subsurface ocean question will be answered someday, one way or another. Future missions, if they are funded, if they are built, if they make the 9-year journey, will send back images of the far side of Pluto that New Horizons never saw, because it only had one pass. They will map the surface from orbit. They may land. That story is ahead of us, unwritten. Tonight there is only this, a world at the edge of everything, luminous in the dark, its heart still turning, its haze still blue. The nitrogen is cold. The ice is still. The stars above Sputnik Planitia are the same stars above you now, only rearranged by 39 astronomical units of parallax, shifted slightly in the sky, the same light arriving from the same sources, connecting the place you are lying to the place you have been traveling tonight. You have been to Pluto. You have seen the heart. You have felt the silence of the bladed terrain, the slow luminescence of the convection plane, the dark mouth of Right Mons open to the sky, the reddish stain on Charon's pole, the 4 tumbling moons catching starlight as they spin. You have been to the edge of the solar system and found it full. If this kind of story is what you come back to, if this is the kind of darkness you choose to fall asleep inside, then please leave a like and subscribe and turn on the notification bell so this channel can keep going. Every single one matters. Good night.